The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Last time we defined the expected value of a random variable, and we talked about a lot of ways it could be computed. We proved all sorts of equivalent definitions. Today we're going to keep talking about expectation, and we're going to start with an example that talks about the expected number of events that you expect to have occur. And it's a generalization of what we did with Chinese appetizer and hat check from last time. We're going to call this theorem 1. If you have a probability space, S, and you've got a collection of n events, let's call them A1 through AN. And these are just subsets of S. Then the expected number of events to occur of these events is simply the sum of I equals 1 to n of the probability of the ith event occurring. So you just sum up the probabilities that the events occur, and that tells you the expected number of events that will occur. So a very simple formula. So for example, AI might be the event that the ith man gets the right hat back from last time. Or it could be the event that the ith person gets the right appetizer back at the Chinese restaurant after we spin the wheel in the center. So we're going to prove this, and the proof is very similar to what we did last time when we figured out the expected number of people to get the right hat back. In particular, we're going to start by setting up an indicator variable, t sub I, that tells us whether or not the ith event, a sub I, occurs. So we define t sub I, and it's a function of a sample point, to be 1 if the sample point is in the ith event, meaning the ith event occurs, and 0 otherwise. And this is just another way of saying that t sub I is 1 if and only if a sub I happens or occurs. Okay? Now, what we care about is the number of events that occur. And we get that just by summing up the t sub I. So we'll let t be t1 plus t2 plus tn. All right, and that'll count, because we'll get a 1 every time an event occurs. By adding those up, we'll get the number of events that occur. All right, now we care about the expected value of t, the expected number of events to occur. And I claim that's just the sum I equals 1 to n of the expected value of ti. Why is that true? Why is the expected value the sum of the expected value of t the sum of the expected values of the t sub I? Linearity of expectation. Now, did we need the t sub i's to be independent events for that? No. OK, very good. Now, the expected value of ti is really easy to evaluate. It's just a 0, 1 variable, so it's just the probability that ti is 1. Because it's 1 times this plus 0 times the probability at 0, and that cancels out. And the event that ti equals 1 is just the situation where the ith event occurs. All right, because ti equals 1 is the case that ai occurs. That's what it is. All right, so we've shown that the expected number of events to occur is simply the sum of the probabilities that the events occur. So very simple formula, very handy. And you don't need independence for that. Any questions about that? All right, we're going to use that theorem a lot today. As a simple example, suppose we flip n fair coins. And we let AI be the event that the ith coin is heads. And suppose we want to know the expected number of heads in the n flips. Well, we can use this theorem. All right, the expected number of heads is just going to be the sum of the probabilities that each coin is a heads. So let's do that. T is the number of heads. We want to know the expected value of t. And from theorem 1, that's just probability the first coin is heads plus the probability the second coin is heads. And the same out to the probability the nth coin is heads. What's the probability the first coin is heads? And half. Probability the second coin is heads is a half. Probability the last coin is heads is a half. And so the expected number of heads, we add up a half n times, is just n over 2. Of course, you all knew that if you flip n fair coins, the expected number of heads is half of them. But that's a very simple way to prove it. Did we need the coin tosses to be mutually independent to conclude that? No. I could have glued them together in some weird way. In fact, I could have glued some face up and some face down and done weird things, and you still expect n over 2 heads, even if they're glued together in strange ways. Because I don't need independence for linearity of expectation to prove this. OK, now that's the easy way to prove, to evaluate the expected number of heads. There is a hard way to do it. And let me set that up. We could start from the definition, a different definition, namely that the expected value of t is the sum from I equals 0 to n, I times the probability that you have I heads. This would be a natural way to compute the expected number of heads. You add up the case where there's 0 heads times the probability of 0, 1 times the probability of 1 head, 2 times the probability of 2 heads, and so forth. That's one of the first definitions of expectation. All right, so let's keep trying to do this. What is the probability of getting I heads? And now I'm going to have to assume mutual independence, actually. Now I'm going to need mutual independence. So already this method isn't as good, because I had to make that assumption to answer this question. If you don't make that assumption, you can't answer that question. What's the probability of getting I heads out of n? Yeah?
Half to the nth power.
Yep.
Times n choose I.
Yes, because if you look at the sample space, there are 2 to the n sample points, all equally likely. They're all probability 2 to the minus n. And there's n choose I of them that have I heads. And now you'd have to evaluate that sum, which is sort of a pain. You know, that one won't come to mind readily. So you might say, oh, I reached sort of a dead end here. But in fact, the answer was easy to get using this method. In fact, we've actually proved an identity here. Because we know the answer is n over 2, we've just proved that this messy thing is n over 2. All right, in fact, we can multiply by 2 to the n here. We have proved, using probability theory and theorem 1 over there, that the sum of I, n choose I, equals n 2 to the n minus 1. Right, just multiply by 2 to the n on each side. So we've given a probability-based proof of this identity, which is sort of hard to do otherwise. Can be harder to do. Any questions about that? So again, if it comes time for a homework problem or a test problem, if it naturally divides up in this way, where you can take a random variable when you've got a computed expectation and make it a sum of indicator variables, if that is a natural thing to do it that way, because it's so much easier than trying to go from the definition, because you might encounter nasty things like that you got to evaluate. OK. So in this case, we flipped n coins. We expect n over 2 heads. In the hat check, in Chinese appetizer problems, we had n hats or n appetizers. We expected to get 1 back to the right person, so a smaller expected value. For some problems, the expected value is even less. The expected number of events to occur is less than 1. In fact, it might be much less than 1. Now, in those cases, it turns out that the expected value is an upper bound on the probability that any event, or that one or more events occur. And we're going to state this as theorem 2. The probability that at least one event occurs is always upper bounded by the expected number of events to occur. Now, this theorem is pretty useless if the expected number of events to occur is bigger than 1, because all probabilities are at most 1. But if the expected number of events to occur is small, something much less than 1, this is a pretty useful bound. All right, so let's prove that. Well, the expected value of t, in this case, we'll use one of the definitions we have of expected value, namely the one where you sum from I equals 1 to infinity of the probability t is greater than or equal to I. Now, what did we have to know about t to use that definition? That doesn't work for all random variables t. What condition do I have on t to be able to use this one? Anybody remember? Yeah.
Must be defined on the natural numbers.
T must be defined on the natural numbers. If it is, I can use this very simple definition. And is t defined on the natural numbers here? Is the range of t natural numbers? Well, I'm counting the number of events that occurred. Could be 0, 1, 2, 3, 4. It has to be a natural number, so it's OK. So I can use this definition. Now, this is summing up probability t is at least 1 plus probability t is at least 2, and so forth. I'm just going to use the first term. This is at least the size of the first term, because probabilities are non-negative. All right, so I'm just going to throw away all the terms after the first and conclude that this is at least the probability t is bigger than or equal to 1, and I'm done. I just look at it in reverse. The probability of at least one event occurring is at most the expected value. Very simple. In fact, there's a very quick corollary here. The probability at least one event occurs is at most the sum of the probabilities of the events. And the proof there is just plugging in theorem 1, okay, because the expected value is the sum of the probabilities. So we just plug in theorem 1 for the expected value, because it's just that. Any questions about the proof? Very simple. Now, this theorem is very useful in situations where you're trying to upper bound the probability of some kind of disaster or something bad happening. For example, suppose you want to compute the probability that a nuclear plant melts down. Now, actually, the government does this. They got to figure this thing out, because if it's a high probability, well, we're not going to allow anybody to build them. And the way they do it is they convene a panel of experts. They get some people from various good universities, and they bring them down to Washington. And they have them figure out every way they can think of that a meltdown could occur, every possible event that would lead to a meltdown. And then they'd have them figure out the probability for each one of those events. For example, A1 could be the event that the operator goes crazy and makes it melt down. A2 could be the event that an earthquake hits and the coolant pipes are ruptured, and then you got a meltdown. A3 is the event the terrorists shoot their way in and cause a meltdown. All right, so you got a lot of possibilities for how the thing can melt down. And then they compute the probabilities, and then they add them up, just using this result. And they say, well, the probability that a meltdown-causing event, or one or more, occurs is at most this small number. And hopefully it's small. So for example, suppose there's 100 ways that a meltdown could occur. 100 things that could cause a meltdown. And each one happens with probability 1 in a million. What can you say about the probability that a meltdown occurs? You got 100 ways it can happen only. Each is a 1 in a million chance. What's the probability a meltdown occurs? 1 in 10,000. Because you're adding up 1 in a million 100 times. N's 100. Each of these is 1 in a million. So you get 100 over a million is 1 in 10,000. And so then they publish a report that says the chance of this reactor melting down is 1 in 10,000. Now, what if I've got 100 reactors? What's the chance that at least one of them melts down? 1 in 100, because I got 100 over 10,000. Same theorem. So there's a 1 in 100 chance something melts down somewhere, at most. And that's, well, that one's, hopefully the numbers are better than that. OK, same thing. If you bought 100 lottery tickets, each a 1 in a million chance, you got a 1 in 10,000 chance of winning, at most. All right, so simple fact, but powerful and used a lot in practice. And this is sort of the good case when the expected number of events that are bad to happen is small, like a lot less than 1. But what if the expected number of events to happen is big? Say it's 10. All right, say this government panel gets together and they add up all the probabilities and it comes out to be 10. Well, doesn't sound so good, if that's the case, but is it necessarily bad? Does it necessarily mean that you're going to have a meltdown? So for example, let's say there's 1,000 ways you could melt down. And let's say that the probability of each one is 1 in 100. So the expected number of things that could happen to cause a meltdown is 10. Am I guaranteed we're going to melt down? No. Can anybody think of a way where it's unlikely we're going to melt down, but respect these values here? Hypothetically. Is there any chance that it's still unlikely to have a meltdown? Can I think of a way? Yeah?
They all happen at the same time.
They all happen at the same time. All right, now the examples I gave, the terrorist, the earthquake, and the crazy operator, put that on the side. If they all happen together, when any one happens, the others have to happen. All right, so we can express that as, for all ij, probability of the ith event happening given the jth event happening is 1. So total dependence. What's the probability of a meltdown in that scenario? What's the probability one of those meltdown-inducing events occurs? They all happen at once.
100.
1 in 100. Because it's the same as the probability of the first event happening, which by definition was 1 in 100. OK, so it could be that the probability of a meltdown is small. But it might not be as well. There's no way, given this, to know. OK. What if I change? In fact, this is like Chinese appetizer, right? If one person gets their appetizer back, everybody does. So there are circumstances where you have the total dependence like that. OK? Let's say I change a little bit, and I don't do this scenario. In fact, say I tell you the events are mutually independent. but you expect 10 to occur. I mean, do you sleep at night now? Of course, 1% is still a pretty high number, but how many people think that if they're mutually independent and you expect 10, that no matter what, there's at least a 50% chance of a meltdown? Anybody? Oh, okay. In fact, if you expect 10 and they're mutually independent, a meltdown is a virtual certainty. The chance you don't melt down is less than 1 in 22,000. All right? For sure, something will occur that's bad. And this is a theorem that we call Murphy's Law. And Murphy's Law, probably you've all heard of it. It says, it's a famous saying, if something can go wrong, it will go wrong. All right? And we're going to see why that's true, at least in our circumstances here. It's a pretty powerful theorem. If you have mutually independent events A1 through AN, then the probability that none of them occur, t equals 0, is upper bounded by e to the minus expected number of events to occur. All right, so if I expect 10 to occur, the chance that none do is upper bounded by e to the minus 10, which is very small, which means almost surely one of the events or more will occur. All right, and that's sort of bad news in this case. So let's prove that. Well, the probability that t equals 0 is the same as the probability that A1 does not occur, and A2 does not occur, and all the way to AN does not occur. And I claim this is the probability, the product of the probabilities they don't occur. So I'm taking the product, I equals 1 to n, of the probability that AI does not occur. Now, why can I make that step? Yeah, independence, right? This is the product rule for independent events. All right? All right, now the probability that AI does not occur is simply 1 minus the probability it does occur. All right, and now I'm going to use a simple fact, which is that for any number x, 1 minus x is at most e to the minus x. Just a simple fact from algebra. So I've got 1 minus, I'm going to treat this as the x. So this is, at most, e to the minus probability of AI, using that fact. And now I'll take the product and put it to a sum in the exponent. Okay, and then the sum of the probabilities of the events is just the expected value. That was theorem 1 that I just erased. So this is e to the minus expected number of events to occur. All right, so not too hard a proof. We had to use that, fact, but that gets the expected number of events to occur in the exponent. So a simple corollary is the case when we expect 10 events to occur. So if we expect 10 or more mutually independent events to occur, the probability that no event occurs is at most e to the minus 10, which is less than 1 over 22,000. Okay, now there's not even any dependence on n here. Right? Nothing to do with the number of possible events, just if you expect 10 of them to occur, you know, you're pretty sure one of them will. And this explains why you see weird coincidences, or people sometimes see what they think are miracles. Because out in the real world, there's billions of possible weird things that could happen. You just can create all sorts of crazy possibilities. And each one might be 1 in a billion chance of actually happening. But you got billions that could have. And if they're all mutually independent because you made up all these different things, then you expect some of them to happen. And so you should, in fact, you're going to know that for sure some of those weird things are going to happen. At least the chance that no weird thing happens is 1 in 22,000. All right? And this can be, you know, why somebody will go along and say, you know, oh my goodness, you won't believe what happened, the coincidence. You know, and it's like, wow, the chance of that happening was 1 in a billion. It must have been a miracle or an act of God that this happened. But you're not thinking about the other 10 billion things that didn't happen. Okay? So for sure, some of those things are going to happen. You know, it's not likely that I'm going to win megabucks next week. But somebody's going to win. Right? If enough people play, and it's more than the probability that, 1 over the probability that you're going to win, then it's very likely somebody will win if everybody is guessing randomly. All right, any questions about what we're doing? Yeah. All right, so this is amazingly powerful, this result. In fact, it's so powerful that it's going to let me read somebody's mind in the class. We're going to do a little card trick here. Now, the way this card trick works, it's a little complicated. I'm going to need a volunteer, probably one of you guys down front. All right, we'll get you. And one of your buddies is going to keep you honest for me here. I'm going to reveal, first I'm going to let you shuffle the deck. So go ahead and shuffle it, do whatever you want to. It's a normal deck. It's got 52 cards and 2 jokers. And I don't care what order they're in. I'm going to turn over the cards one at a time. Now I'm going to ask you to pick a number from 1 to 9 ahead of time. Don't tell me or anybody else. In fact, I'm going to want you guys to play along too. We're going to see where we all end up here. And that's your starting number. And as I turn over the cards one at a time, say you started with a 3 was the number you had in mind. On the 3rd card I show, that becomes your card. You don't tell me or jump up or down or anything. But that's your card. And say it's a 4 of diamonds. Now 4 replace the 3 in your mind. And you count 4 more cards. Then that becomes your card. Now say that's a jack, or a face card, or a 10, or a joker. 10 face card and jokers all count as 1, just like an ace counts as 1. And so then the next card would be your card, because you count 1. And we keep on going until you have a card, maybe it's a 7, but there's only 4 cards left in the deck. And so you don't get a new one. And your last card is the 7. All right? And then you're going to write that down here, not showing me. And you're going to do this, maybe do this with a friend over there. And you're going to make sure you count right on the deck, because if you screw up the counting, it's going to be hard for me to read your mind. So just to make sure we all understand this, let me write the rules down here, because I want the whole class to pick a number from 1 to 9 and play the same game. And we're going to see what happens. So let me show you the rules again, just to make sure everybody understands. So say we say the deck starts out like this. I got a 4, a 5. So my first few cards of the deck go like this. 10 equals a 1. Then I got a queen equals a 1. 3, 7, 6, 4, 2. Say it's a small deck. I'm going to use 54 cards. And say your chosen number to start, you start with a 3. So you're going to, as I show the cards, you're going to count 1, 2, 3. That becomes your new card. Then you're going to count 1, 2. That becomes your card. It's a 10, so you convert it to a 1. We're only doing single-digit numbers. Go to 1, that becomes your card. Queen converts to a 1. You go 1, that becomes your card. 3, 1, 2, 3. That becomes your card. And you can't get 4. So you remember the final card. All right, does everybody understand what you're supposed to do? Because we're going to do 54 cards of this. All right, maybe we get the TAs to play along here. And as you do it, maybe you want to talk to your buddy, make sure you got it worked out there. All right, so let me, and if I can read your mind, maybe we'll have a gift certificate or something. All right, so you shuffled the deck? Got it good? All righty, so I'm going to start revealing the cards one at a time, so you guys play along, quietly in your mind. And see if we can concentrate long enough. Aces are 1. Jacks are 1. Tens are 1. Tens are 1. Halfway done. Jokers are 1. Okay, that's the last card. So remember the last one that was yours. You better go check with your buddy to make sure you guys agree on the counting there. And then write it down. Don't tell me, because I'm going to read your mind. I'm going to tell you. This is not good. They're arguing over the last card. I'll have to read one of your minds. What's that? The 11 of clubs. That's a hard one to predict. All right, make your best guess and write it down. Don't tell me, write it down. You got 2, well, write them both. I'll predict one of them. Yeah, I've never had a dispute on what the, because if you start with the same position, you got to wind up in the same position. All right, you wrote it down? All right, now think about your number really hard. We'll take yours. I'll trust you there. Think about it really hard, because I need the brain waves to come over and, read the mind here. All right. Well, yeah. Boy, I'm getting a really strong signal on the last card. Maybe, I don't know, maybe it's really powerful. I'm going to say it's the Queen of Hearts. Is that right? Both were the Queen of, oh, you were trying to screw me up, mess with me. So you both got the Queen of Hearts. Oh, you did. So how many people got the Queen of Hearts? Oh, wow. How many people did not get the Queen of Hearts? Somebody, okay. Now, there's a chance you did it legitimately, but usually with the deck, we're all going to get the same last card. Now, in this case, it happened to be the very last card. That is typically not the case. So, very good. So I read your mind, so you guys get the gift certificates here. Very good. One for you and your sponsor there. All right, so it's clear how I read his mind, right? Because I got the same number everybody did. And somehow it doesn't matter where we started, we all had the same card at the end. How is that possible? There's 9 different starting points. Why don't we wind up at 9 different places? And why isn't there a 1 in 9 chance that I guess his card? Why do we all wind up in the same place? Any thoughts? Yeah?
The same card after that, you stay the same time.
That's right. If ever we had the same card, then we're going to track forever and finish on the same card. But why should we ever get the same card? I mean, what are the chances of that we land on the same card? Why don't we just keep missing each other? It's a 1 in 9 chance or something. I don't know. Why don't we keep missing?
It seems like there are enough low cards that you just move slowly along, and eventually you're going to intersect.
Yeah, I did make a lot of 1s in the deck. If I'd have made all these face cards be 10s, the chances of my reading your mind go down. Why do they go down? What does it have to do? Why did I put a lot of 1s in the deck?
It goes on longer.
What's that?
The game goes on longer.
The game goes on longer, so there's more chances to hit together. Because at any given time, you've got your card, I've got mine. If mine's behind you, I got a chance to land on you. And if you're behind me in the deck, you got a chance to land on me with your number. And if the numbers are smaller, there's more chances to land on each other. And it is true that on any given chance, the chances are low that we land on the same card. But there's a lot of chances. And if there's a lot more chances than the probability of landing on each other, we've got Murphy's Law. Right? If you got a lot of chances, and they're not less likely than the number of chances, or the inverse of that, then we expect to have a bunch of times where we're going to land on each other, and therefore, very high probability we do. Okay, now, that was a little hand-wavy. And in fact, there's a reason it was hand-wavy. Why doesn't Murphy's Law really apply in this case, really mathematically apply? Yeah?
They're not mutually independent. Once you draw one card,
it's not coming back.
That's correct. And it means that the knowledge that we haven't collided yet tells me something about the cards we've seen. Not a lot, but something maybe. And it's a finite deck, which tells me something about the cards that are coming, and it might influence the probability that we land together, the next person who's jumping on the deck. And so the events of, like for example, in this case, we'd let AI be the event of a collision on the ith jump. And there's about 20 jumps in this game, 10 for each of us, expected. So AI is the event that we collide on the ith jump. These events are not necessarily mutually independent. Now, if I had an infinite deck, or a deck with replacement, so every card is equally likely to come next no matter what's come in the past, now you can start getting some mutual independence here. And then you can start really applying the theorem. All right, now in this case, you don't expect 10 things to happen. You expect a few. But that's good enough that, in fact, so we did a computer simulation once, and I got about a 90% chance that we'll all be on the same card. So I have a pretty good chance that I'm going to guess right. And so far, I haven't guessed wrong. But it will happen someday that we'll start with a different first number, and we will miss at the end, because there'll be 2 possible outcomes, just the way it works out with 52 cards. Now, of course, if we have more cards, or I made more things be 1s instead of 9s, say, my odds go up, because the number of events I've got, the number of chances to collide, increases. And the chance of hitting when I jump also increases. Any questions on that game? OK, so the point of all this is that if the expected number of events to occur is small, then it's an upper bound on the probability that something happens, whether they're independent or not. If the expected number of events to occur is bigger than 1, large, and if the events are mutually independent, then you can be sure one of those events is going to occur. Very, very likely. One of them will occur, and that's Murphy's law. All right, any questions about numbers of events to occur? All right. OK, we'll talk more about the probability and the numbers of events that occur next time. But before we do that, I want to talk about some more useful facts about expectation. Now, we know from linearity of expectation that the expected value of a sum of random variables is the sum of the expected values of the random variables. Now we're going to look at the expected value of a product of random variables. And it turns out there's a very nice rule for that. We theorem 4, and it's the product rule for expectation. And it says that if your random variables are independent, if R1 and R2 are independent, then the expected value of their product, which is also a random variable, is simply the product of the expected values. So it's sort of the equivalent thing to linearity of expectation, except we're doing products, and you need independence. Now, the proof of this is not too hard, and it's in the book, so we're not going to do it in class. But we can give an example. Say we roll 2 6-sided, fair, and independent dice. And I want to know what's the expected product of the dice. All right, so we're going to let R1 be the value on the first die, and R2 will be the value on the second one. And the expected value of the product is the product of the expectations. And we already know the expected value of a single die is 7/2. So we get 7/2 times 7/2 is 49/4 or 12 1/4. All right, so it's easy to compute the expected product of two dice. Any questions about that? Much easier than looking at all 36 outcomes to use this rule. Now, what if the dice were rigged, glued together somehow, so they always came up the same? Would the expected product be 12 1/4 then? No? Why not? Why wouldn't it be the case? Why isn't the expected value of R1 squared the square of the expected value of R1? Why, isn't that what this says?
They're independent.
They're not independent. R1 is not independent of R1. In fact, it's the same thing. All right, and you need independence for that to be the case. All right, so a non-example. The expected value of R1 times R1 is the expected value of R1 squared. And to do that, we've got to go back to the basics. We're taking the 6 possible values of R1, I equals 1 to 6, I squared, because we're squaring it, times the probability R1 equals I. And each of those probabilities is 1/6, so we get a 6 times 1 plus 4 plus 9 plus 16 plus 25 plus 36. And if you add all that up, you get 15 1/6, which is not 3 1/2 squared, which is expected value of R1 squared. All right, so the expected value of the square is not necessarily the square of the expectation. And there, because a random variable is not independent of itself generally. Okay, any questions there? All right, there's a couple quick corollaries. The first is you can take this rule and apply it to many random variables, as long as they're mutually independent. So if R1, R2, out to Rn are mutually independent, then the expected value of their product is the product of the expected values. And the proof is just by induction on the number of random variables. So that's pretty easy. There's another easy corollary. And that says for any constants, constant values, A and B, and any random variable R, the expected value of A times R plus B is simply A times the expected value of R plus B. And the reason that's true, well, the sum works because of linearity of expectation for the sum. You can think of B as a random variable that just always has the value B. And the A comes out in front because you could think of it as a random variable that always has the value A, and that's independent of any other random variable because it never changes. So by the product rule, the A can come out. Now you've got to prove all that, but it's not too hard and not especially interesting, so we won't do that here. Okay, any questions about those? All right. Okay, so we got a rule for computing the sum of random variables, a rule for the product of random variables. What about a rule for the ratio of random variables? Let's look at that. Okay, so is this a corollary? In fact, let's take the inverse of random variable. Is the expected value of 1 over r equal to 1 over the expected value of r for any random variable r? Some folks saying yes, some saying no. What do you think? Is that true? Got some, well, I got a mix. Yes. How many say yes? How many say no? Oh, more no's. All right, somebody tell me why that's not true. Give me, who'd like to give me an example? What's an example there? It'll be very convincing. Yeah?
I mean, I don't think it's one that would be immediately obvious, but I think if R is the result of the roll of a die, I don't think it works out.
So it's 50 chance of, oh, I see. So I take the average of 1 over I. That's sort of hard to compute. I got to do the sixth harmonic number and then invert it. There's an easier way to show that this is false. Yeah? Yeah, if the expected value equals 0, right, which could happen if r is +1 or -1 equally likely. All right, so here's an example here. So r equals 1 with probability 1/2, and -1 with probability 1/2. So the expected value of r is 0. So that blows up. That's infinity. What's the expected value of 1 over r? Well, 1 over 1 and 1 over -1, it's the same, equals 0. And this would say, 0 equals 1 over 0. That's not true. So this is false. It is not true for every random variable. All right. So once you see this example, it's just obviously not true. In fact, there's very few random variables for which this is true. Even an indicator random variable, right? So it's 1 with probability 1/2 and 0 with probability 1/2. Then the expected value of 1 over r is infinite. 1 over the expected value of r is 2. All right? Or so, yeah, it's 2. So it's clearly not true. All right, let's do another one. What about this potential corollary? Given independent random variables, r and t, if the expected value of r over t is bigger than 1, then the expected value of r is bigger than the expected value of t. And let me even give you a potential proof of this. See if you like this proof. Well, let's assume the expected value of r over t is bigger than 1. And let's multiply both sides by the expected value of t. All right, and well, the product rule says that this is just the expected value of r over t times t, which is just the expected value of r, because the t's cancel. All right, so I gave you a proof. Anybody have any quibbles with this proof? Yeah? That's a big problem. R over t is not independent of t. In fact, if t is very big, likely that r over t is small. So we can't do that step. We can't use the independence here to go from here to here. That's wrong. There's actually another big problem with this proof. Anybody see another problem? Yeah? Yeah. If the expected value of t is negative, I would end up doing that. So that step's wrong. So basically, this is a pretty lousy proof. Every step is wrong. So this is not a good one to use. And in fact, the theorem is wrong. Not only is the proof wrong, but the result is wrong. It's not true. And we can see examples. We'll do some examples in a minute. Now, the amazing thing is that despite the fact that this is just blatantly wrong, it is used all the time in research papers. And let me give you a famous example. This is a case of a actually pretty well-known paper written by some very famous computer science professors at Berkeley. And let me show you what they did. And this is so that you will never do this. They were trying to compare two instruction sets way back in the day. And they were comparing the RISC architecture to something called the Z8002. And they were proponents of RISC. And they were using this to prove that it was a better way to do things. So they had a bunch of benchmark problems. There are probably 20 or so in the paper. And I'm not going to do all 20 here. I'm going to give you a flavor for what the data showed. And then they looked at the code size for RISC and the other guy, Z8002. And then they took the ratio. All right. So the first problem was called E-string search, whatever that is, but it was some benchmark problem out there at the time. And the code length on RISC was 150. Say, I've changed these numbers a little bit to make them simpler. Code length here on the Z8002 is 120. The ratio is 0.8. So for this problem, you're trying to get low short code, so this was a better way to go to support that. And they had something called F-bit test. And here you have 120 lines. Here's 180. So in this case, RISC is better. So the ratio of that way to this way would be 1.5. And they had computing an Ackermann function. And that was 150 and 300. So a big win for RISC, ratio of 2. And then they had something called recursive sorting problem. This is a hard problem. There's 2,800 lines on RISC, 1,400 on the old way, ratio of 0.5, 0.5. And there was a bunch more, which I'm not going to go through. But their analysis, what they did is they took the ratio, and then they averaged it. And so when you do this, you get an average of, well, 2.3, 4.3, 4.8 over 4 is 1.2. So the conclusion is that on average, code in this framework is 20% longer than the code on RISC. Therefore, clearly, RISC is a better way to go. Your code, on average, will be shorter. Using the Z8002, on average, the code will be 20% longer. Makes perfect sense, right? In fact, this is one of the most common things that it's done when people are comparing two systems. Now, just one problem with this approach, and that's that it's completely bogus. Completely bogus. You cannot conclude this, make this conclusion. So their conclusion, they concluded that Z8002 programs are 20% longer on average. Okay? Everybody understands the reasoning why, right? Take the ratio of all the test cases, average them up, and you get the average ratio. All right? Now, there could be some hint why this is bogus. I mean, if I just looked at, if I took and summed these numbers, if I add all those numbers up, I get 3220, and all these, I get 2000. Well, risk code is not looking shorter if I do that. Looking longer. But, you know, all that gain, all the loss for risk is in this one problem, and maybe it's not fair to do that. And that's why when people have data like this, they just take the ratios, because now it would be, you know, if I just took the average code length and took the ratio of that, it's not fair, because one problem just wiped out the whole thing. Right? I might as well not even do it. And they want every problem to count equally. And that's why they take the ratio, to make them all count equally. But let's do one more thing here. Let's look at what happens if we take the ratio of risk to the Z 8002. Let me make some room for that. So this column was Z 8002 over risk. What if I just did this, risk over the Z 8002? I mean, the answer should come out to 1 over 1.2, right? That's what we expect, because I'm just turning it upside down. Well, I get 1.25 here. These are just being inverted. Here I got 2/3, 0.67. Here I get a half. Here I get 2. All right, let's add those up. I get 1.92, 2.42, 4.42. Divide by 4, wow, I get 1.1 something. Which says, well, that on average risk is 10% longer than the other one. So same analysis says that risk programs are 10% longer on average. Now, the beauty of this method is that you can make any conclusion you want seem reasonable, typically. You could have the exact same data, and if you want risk to look better, you do it this way. If you want risk to look worse, you do it that way. You see? Is that possible? Is it possible for one to be 20% longer than the other on average, but the other to be 10% longer on average? How many people think that's possible? We had some weird things happen in this class. But that's not possible. All right, that can't happen. These conclusions are both bogus. All right? Now, I am not teaching you this so that later when you're doing your PhD thesis and it's down to the wire and you need a conclusion to be proved, good news, you can prove it. All right? No matter what your conclusion is, you can prove it. All right, that's not why we're doing this. We're doing this so you can spot the flaw in this whole setup, and that you'll never do this, and you'll see it when other people do, because people do it all the time. All right? So let's try to put some formality under this in terms of probability, because when you start talking about averages, really think about expectations of random variables and stuff. So let's try to view this as a probability problem and see if we can shed some light on what's going on here, because it sure seemed reasonable. All right, so let's let x be the benchmark. And maybe that'll be something in the sample space, an outcome in the sample space. Let's let Rx be the code length for risk on X, and Zx be the code length for the other processor on X. And then we'll let probability of X, we'll define a probability of seeing X. The probability, that's our problem we're looking at. And typically, you might assume that it's uniform. the distribution there. We need this to be able to define an expected value for R and for Z. All right, now, what they're doing in the paper, well, what really is happening here is instead of this, they have the expected value of Z over R is 1.2. That is what they can conclude. That does not mean that the expected value of Z is 1.2 the expected value of R, which is what they conclude, that Z8002 code is 20% longer than RISC code. This is true. That is not implied. And why not? That's just actually what this corollary was doing, right? Really, it's just what they made the same false assumption as happened in the corollary. You can't multiply both sides here by the expected value of R and then get the expected value of Z. Now, of course, if you ask them, they would have known that. But they didn't even think through that. They just used the standard method of taking the expected value of a ratio. So this is fair to conclude. But as we saw, the expected value of R over Z was 1.1. So both of these can be true at the same time. That's fine. But you can't make the conclusions that they tried to make. All right? And here's another in fact, in this case, if we had a uniform distribution, the expected value of R is like 805 for uniform. And the expected value of Z is 500. All right, and that's all you can conclude if you're taking a uniform distribution. In which case, of course, if they're promoting RISC, well, you don't like that conclusion. So it's better to get this one. Not that I don't think it was intentional, of course, but it's nice that it came out that way. All right, here's another example that really makes it painfully clear why you never want to do this. So a really simple case, just generic variables R and Z. And I got two problems only, problem 1, problem 2. R is 2 for problem 1, and Z is 1, and they reverse on problem 2. Z over R is 2.5. All right. R over Z, just the reverse. All right. Now, the expected value of R over Z here is 2 plus 1/2 divided by 2 is 1 1/4. And what's the expected value of Z over R? The average of these is 1 1/4. What's the average of these? Same thing, 1 1/4. So never, ever take averages of ratios without really knowing what you're doing. OK? Any questions? Yeah?
What would be like the word explanation of expected value of Z over R? Like, what is that?
That is the average of the ratio. It is not the ratio of the average. They are very different things. And you can see how you get caught up into that because you got linear rate of expectation, you got the product rule for expectation. You do not have a rule that says this implies that. Which two?
Z over R.
Well, in this case, they're 1, but they wouldn't. I don't think that'll be true in general.
Does
That
that
would
give
not
you
be.
information?
They give you information. It may not be the information you want. Like you may want to, it wouldn't imply that, which is what you're after in some sense. But it gives you some information. It's the expected average ratio. The problem is the human brain goes right from there to here. That's just you do. Right? It's hard to help yourself from doing it. And it's not true. That's the problem. In fact, we have a version of this in one of the homework questions, which is true. but it's a special version of it where you can say something positive. Any questions about this? So anybody ever shows you an average of ratios, you want the light to go off and say, danger, danger, think what's happening here, okay? Or if you're ever analyzing data to compare two systems. Okay. So we talked a lot about expectation. We've seen a lot of ways of computing it. We've done a lot of examples. For the rest of today and for next time, we're going to talk about deviations from the expected value. Now, for some random variables, they are very likely to take on values that are near their expectation. For example, if I flip 100 coins and say they're fair and mutually independent, we know that the expected number of heads is 50. Does anybody remember the probability of getting far from that, namely having 25 or fewer heads or 75 or more heads? Remember we did that? Was it a couple weeks ago? Is it likely to have 25 or fewer heads? Less than 1 in a million. Yeah, it was 1 in 5 million or something. I don't know, some horribly small number. So if I flip 100 coins, I expect to get 50 heads, and I am very likely to get close to 50 heads. I'm not going to be 25 off. All right? And then the example we had in recitation, you got a noisy channel, and you expect an error rate, 1% of your 10,000 bits to be corrupted. The chance of getting 2% corrupted was like, what is it, 2 to the minus 60 or something? Extremely unlikely to be far from the expected value. But there's other cases where you could well be far from the expected value. Can anybody remember an example we've done where you are almost surely way off your expected value for a random variable? Anybody remember an example we did that has that feature?
The appetizer thing.
The appetizer. Let's see. OK, appetizers, you expect 1. And you're almost certain to be 0. Or you're almost certain to be 0, and you have a chance of being n. So if you count 0 as being close to 1, you're likely to be close to your expectation, because you're likely to be 0, and you expect 1. Remember that noisy channel problem? The latency problem across a channel? And we showed that the expected latency was infinite, but 99% of the time you had 10 milliseconds, something like that. All right, there's an example where almost all the time you are far from your expectation, which is infinite. All right, so there are examples that go both ways. Now, let's look at another couple of examples, and it'll motivate a definition that measures this. All right, say that we've got a simple Bernoulli random variable where the probability that R is 1,000 is 1/2, and the probability that R is minus 1,000 is 1/2. Then the expected value of R is 0. Similarly, we could have another one, S, where the probability that S equals 1 is 1/2, and the probability that S equals minus 1 is 1/2, and the expected value of S is 0. Now, if this was a betting game, and we're talking about dollars, here's where you're wagering $1,000, fair game. Here's where you're wagering $1. Now, in this game, both games are fair. Expected value is 0. But here you're likely to end up near your expected value. Here you're certain to be far, by some measure, from your expected value. And in fact, if you were offered to play a game, you might have a real decision as to which game you played. If you like risk, you might play that game. If you're risk averse, maybe you stick with this game, right? Because what you could lose would be less. All right. Now this motivates the definition of the variance, because it helps mathematicians distinguish between these two cases with a simple statistic. the variance of a random variable, R, is denoted, we'll denote it by var, VAR, of R, is defined as the expected value of the random variable minus its expected value squared. That's sort of a mouthful there, so let's break it down. This is the expected value of R. This is the deviation from the expected value. So this is the deviation from the mean. Then we square it. All right, so that equals the square of the deviation. And then we take the expected value of the square. So the variance equals the expected value of the square of the deviation. All right, in other words, the variance gives us the average of the squares of the amount by which the random variable deviates from its mean. Now, the idea behind this is that if a random variable is likely to deviate from its mean, the variance will be high. And if it's likely to be near its mean, the variance will be low. And so variance can tell us something about the expected deviation. All right, so let's compute the variance for R and S and see what happens. So with R minus the expected value of R, well, that is going to be 1,000, because the expected value is 0, with probability of half, and minus 1,000 with probability of half. Then I square that. Well, I square 1,000, I get 1,000,000 with probability of half. And I square minus 1,000, I get 1,000,000 again with probability of half. And so therefore, the variance of R, well, it's the expected value of this, which is, well, it's always 1,000,000, so it's just 1,000,000. Big. Now, if I were to do this with S, S minus the expected value of S is 1 with probability of half, minus 1 with probability of half. If I square that, well, I get 1 squared is 1, minus 1 squared is 1. And so the variance of S is the expected value of this, and that's just 1. All right, so a big difference in the variance. So the variance being different tells us these random variables are, their distributions are very different, even though their expected values are the same. And the guy with big variance says, hey, we're likely to deviate from the mean here. And so risk-averse people stay away from strategies when they're investing that have high variance. Now, does anybody have any idea why we square the deviation? Why didn't mathematicians, when they figured out this stuff, I don't know how many centuries ago, why didn't they just take the expected deviation? Why do this stupid squaring thing? That only is going to complicate it. Why don't we instead compute the expected value of R minus the mean? Why didn't they do that and call that the variance? Yeah? That's 0. Yeah. Because by linearity of expectation, in fact, the corollary 4-2 or whatever, this is just the expected value of R minus the expected value of the expected value of R. The expected value of a scalar is just that scalar. And that is 0. So the expected deviation from the mean is 0 because of how the mean is defined. It's the midpoint, the weighted midpoint. The times you're high cancel out the times you're low if you got the midpoint right, the mean right. And so this is a useless definition. It's always 0. All right, so mathematicians had to do something to capture this. Now, what would have been the more logical thing to do as the next step? This doesn't work, but what would you think the mathematicians would have done? Absolute value would have made a lot of sense here. Why they didn't do that? Well, you could do that, but it's hard to work with mathematically. You can't prove nice theorems, it turns out. If you put the square in there and make that be the variance, you can prove a theorem about linearity of variance. That if the random variables are independent, then the variance of the sum is the sum of the variances. And mathematicians like that kind of thing. Right? It makes it easier to work with and do things with. Now, there are also other choices. In fact, there's a special name for a weird case where you take the 4th power. You could do that. As long as it's an even power, you could do it. And that's actually called the kurtosis. Sort of sounds like a foot disease. But it's the kurtosis of the random variable. Now, we're not going to worry about that in this class. But we are going to worry about variance. And let me do one more definition, then we'll talk about variance a lot more tomorrow. You know, that square is a bit of a pain, and to get rid of it, they made another definition sort of after the fact called the standard deviation. And standard deviation is defined as follows. For a random variable r, the standard deviation of r is denoted by a sigma of r, and it's just the square root of the variance. Sort of undoing that nasty square root after the fact. So it turns out to be the square root of the expectation of the deviation squared. All right, another name for this you probably have seen. It's the root of the mean of the square of the deviations. And so you get this thing called root mean square, which if any of you have ever done curve fitting or any of those kinds of things in statistics or whatever, this is what you're talking about. And so that's why that expression would have come about. All right, so yeah, so for standard deviation of r, what's the standard deviation of r? 1,000. And in fact, that's pretty close to what you expect the deviation to be. What's the standard deviation of s? 1. Square root of 1 is 1, and that's what you expect its deviation to be. OK, so we'll do more of this tomorrow in recitation.